All right, y'all. Um, London dispersion forces, right? All right, so we've been talking about intermolecular forces, and this is the very first intermolecular force we're going to cover, London dispersion forces. Okay, sounds like it reminds me of that song, the London Bridge is falling down, the falling down, the falling down. All right, okay. So what are these? What are these forces? So this is basically where we're going to have our electrons. So we're really looking at our electrons and how they're distributed in our orbitals or electron cloud area. Okay. So depending on how they are, okay, we can see a temporary dipole. Okay. So basically, what we're going to see here is a couple of different things here. Couple of different things here. Okay. So anytime we have a temporary dipole, all right, these things must happen. So a region, and once again, we're looking at our nucleus, and then we have our electrons surrounding. So at this temporary moment, you're going to have a region to where you're going to have more electrons, okay, in one area, and then on the other end, there's going to be less electrons in one area. So if you have a lot of electrons in one area, we're going to see that we're going to start seeing this partial negative charge, right? And that's because all our electrons are condensed in this one area. It's very electron dense right now. Okay. And so since there's all these electrons in this one particular area, right? It's going to be negative, right? Because, the more electrons we see, it's going to lean towards a negative charge. But right as this is happening, that means that on the other side of the area, all right, in this electron cloud area, our electron density has decreased, right? It's diminished over time, and that's because they all went over here. Okay, so if we have electrons leaving, right, going all over here, what's happening to this side? Well, this side is gone, it's depleted, right? We don't have any electrons over here. And because of that, right, electrons are negative, we're going to have more of a positive charge on this side. Okay. So when we have this partial and positive at the same time, this is where we're going to see this dipole moment occur. Okay. And this is basically, all right, these forces caused by this temporary dipoles, these are London dispersion forces, okay? Or you might hear them be referred to as dispersion forces, or you could just call them London forces, okay? Either way.
Okay.
So if we look at this, let's look at this example here. Okay, let me move me out the way. Okay. So in this example, okay, we're going to look right what these temporary dipole moments are looking like. So for instance, let's say we got helium here. We got some helium atoms all interacting with each other. Okay. And in an instance, okay, we're going to see that our electrons are going to be on one side and it's going to be on the other. Okay, so we're going to have a high electron density on one side and a very low electron density on the other. So when this occurs, right, we see that dipole moment. Okay, and then this dipole moment is going to have some interaction with the other helium elements, okay? And this is going to lead to this attraction, okay? And that attraction is where we see these intermolecular forces start to form, okay? So we're talking about London forces. For instance, let's say we got these three helium elements, right? And this dashed line here is to show that there's an intermolecular force between the three of them. Now, if we break this down, they're looking like this, right? We got our helium, right? This is our nucleus, two protons, two neutrons. And then we know with helium, we got two electrons, right? So temporarily, we're going to see this these electrons kind of shift. In this way, they're going to have this um this unsymmetrical sides to them, right? And when you have this unsymmetrical side to them, this is where we see these moments start to occur. So for instance, let's look here. We got our electrons all on the left side, and because they're all in this specific region, we're going to see that this is where, right, it's going to be more dense. And because it's more electron dense, we start to see this partial negative charge occur, right? More electrons on this side. But since they're all on this side, guess what happened over here? They all gone, right? And if they're all gone, right, very low electron density, right? So because of that, no electrons, it's going to create this partial charge at this moment. So we can see, right, for this particular helium, we got negative and we got this positive. Bam, we got a dipole occurring. But the interaction with the London forces occurs here, okay? So this positive charge is going to be attracted to, guess what? The other negative charge. So if we look at this second helium, right, it looks the exact same thing, right? At this instance, in this case, are electrons, right? So they're not exactly the same, but at this instance, right, the electrons are all creating this partial negative charge for this helium, okay? And since it's creating, the electrons are more towards this side now, the positive end for this helium will be attracted to the negative end of this helium, creating, right, London force right here, right? These London dispersion forces. And then we look at the third, the same thing is occurring, right? At some temporary time, our electrons are all in a specific region, creating this negative charge. So this negative charge will be attracted to, guess what? The other positive charge, okay? So this is where those intermolecular forces are occurring. Now, a couple of different things about London dispersion forces, right? Key thing is these are temporary forces, okay? They're temporary dipoles occurring, all right? So this isn't something that isn't, it's not permanent. This is not a permanent thing. This can happen in an instant and then it could be, gone, just like that, right? Because, right, they're eventually, the electrons are going to be in one region, but they're going to be symmetrical to each other at some point too, all right? But at that time when they are unsymmetrical, this is where we can see London forces start to form here. Now, one thing about London forces that's going to be different from the other forces we talk about here, right, is that everybody and their mama can have a London force, okay? So we're going to see polar molecules be able to have London forces, but also non-polar molecules are able to have London forces. So, and that's because, right, if anytime, right, you got this unsymmetrical density with our electrons, that's the reason why we could have these London forces. And we know that every molecule is going to have some type of electrons in some type of way. So there's a chance that they can have London dispersion forces.
Okay.